Welcome back to Think Thrice. Today we're going to be doing a famous integral called the Gaussian. You may be familiar with the Gaussian from some probability or statistics classes, but basically what it is what we call the normal curve, and we have an integral from negative infinity to infinity of e to the negative x squared dx. So if you'd like, you can go ahead and pause the video, take a minute or two to try to solve this on your own. Otherwise, we're going to jump straight into the solution. So what we notice about this equation is that e to the negative x squared is always greater than 0. Okay, so we're trying to find the area here. It looks like there might be a finite area because I approach 0 as I go to the right, I approach 0 as I go to the left. So let's see if we can work towards something. So if we rename this integral I, we notice that since e to the negative x squared, so our term inside is always greater than 0, then I know that I can be seen as the square root of I squared. Okay, so if I square everything, square the whole integral, take the square root, I should get my same integral back out. So we're going to make use of this fact, and we're going to rewrite our integral. So instead of dealing with I, we're going to deal with I squared. And I squared is going to be the integral from negative infinity to infinity, e to the negative x squared dx, times integral from negative infinity to infinity of e to the negative y squared dy. So notice that we have x in the left and y in the right. So the variable that we choose inside of our integral is fairly arbitrary. So no matter what that is, it's getting solved and worked with as we go through the integral, and we're going to have a number that's popping out the other side. So what we choose isn't super important. I'm going to use x and y so we can think about this as dealing with the Cartesian plane. So we're going from x coordinates from negative infinity to infinity, and y coordinates from negative infinity to infinity. So since the x and the y parameters are independent, it won't impact our expression if I move those together. So what I'm going to go ahead and do is rewrite this as the integral from negative infinity to infinity, and then I'm going to make it a double integral of e to the negative x squared times e to the negative y squared dx dy. And I notice that if I have e to the negative x squared times e to the negative y squared, I can just rewrite that as e to the negative x squared minus y squared. All right, so I have a double integral now that's written in Cartesian coordinates. What you notice if you've taken a multivariable calculus class is that this guy is kind of special. So we can see that this can be written as e to the negative x squared plus y squared. So this should be jumping out to us. This looks like something we can try polar coordinates with. Okay, so we're going to go ahead and try polar coordinates. So what we're going to do is we're going to make x equal to r cosine theta, y is equal to r sine theta, and we notice that x squared plus y squared is equal to r squared cosine squared of theta plus r squared sine squared of theta, which is just equal to r squared times sine squared of theta plus cosine squared of theta. And if you remember your trig identities, this guy is just equal to 1. So that whole expression, x squared plus y squared, is now just r squared. Okay, we're dealing with the entire Cartesian plane. So that means we're going to be dealing with r values from 0 to potentially infinity. So this is going to be an improper integral. And we're going to be dealing with angles from 0 to 2 pi. So all the way around our circle. So let's go ahead and we'll also note that our dA term is now going to be r dr d theta dr. Okay, so let's rewrite our integral now. We have this integral above is now going to be the integral over r on the outside, so 0 to infinity, and then our integral from 0 to 2 pi times e to the negative r squared times r d theta dr. So first we integrate with respect to theta. So this is going to be the integral from 0 to theta, or from 0 to infinity of e to the negative r squared r is just acting like a constant times theta, evaluated from 0 to 2 pi, times r dr, which is going to give us the integral from 0 to theta, infinity of 2 pi minus 0, which is just going to be 2 pi times e to the negative r squared r dr. All right, so we're well on our way here. So next, we're going to do some u substitution. So if I make u equal to negative r squared, du is going to be negative 2r dr, which means that dr is du over negative 2r. So let's go ahead and plug that substitution in. I'm going to get 2 pi times the integral from 0, come back to that a little later, of e to the u times du over negative 2. Our r's are going to cancel. So we can go ahead and pull that out. And we're going to be left with pi times the integral of e to the u, negative pi e to the u du. All right. So let's go ahead and integrate that. So that's going to be negative pi times e to the u. Go ahead and plug our u back in there. So we get negative pi times e to the negative r squared. And that's evaluated from 0 to infinity. So we go ahead and look at that. So I'm going to get negative pi. E to the negative infinity is going to be 0. And e to the 0 is going to be 1. So my answer here is going to be pi. So remember what we just did is we solved I squared. So if we look all the way back up, we can see what we originally did was we were looking at I squared. So I know that I squared is equal to pi. And what we originally said is that my Gaussian, the integral from negative infinity to infinity of e to the negative x squared dx was equal to the square root of I squared, which is going to be the square root of pi. And that's how we come to our solution, that the Gaussian, when we evaluate it, is equal to the square root of pi. I hope you've enjoyed working through this integral with me. If you'd like to see any particular integrals, feel free to submit your problems and I'll go ahead and make some future videos. Otherwise, enjoy mathing and think thrice. Like and subscribe if you enjoyed this content.